So in this video, we're looking at a rectangular channel, and we're going to be using its cylindrical equivalent to help determine the flow rate of the liquid within the channel. So in this channel, it's slanted at some angle, in this case 15 degrees, but it could be any angle. The water's flowing down from point 1 to point 2. It has a width of 0.5 meters, and we're trying to determine the height of the fluid in this case. And so since it's an open channel, the pressure at point 1 and point 2 are the same, so we don't have to worry about this term in Bernoulli's equation. The velocity doesn't change because the cross-sectional area of the channel is the same throughout. And then over here we have this difference in height, and we can express this in terms of theta. And we also want to express it in terms of delta x because we have that on the other side with the frictional heating term. So I don't know why this isn't erasing. There we go. So if we're able to express it in terms of delta x, we can cancel them out. So on the left-hand side, we're going to have g times delta z is going to be equal to negative 4f delta x over d v squared over 2. And delta z is simply going to be delta x times our angle. So we're going to have g delta x times sine of theta is going to be equal to negative 4f delta x. And then these delta x's will cancel, so I'll go ahead and rewrite it now. So we have g sine theta is going to be equal to negative 4f v squared over 2d. So then because the slope is negative, since we're going downhill, the difference in height is negative z2 minus z1. So that will cancel out with the negative sign here. So we're left with 4f v squared over 2d. And then the 4 and the 2 divide, and you're left with 2. You know what, let me read it. We have 2f v squared over d. So when dealing with rectangular channels, we can say that the shear stress along the walls of the rectangular channels is going to be the same as the shear stress along the walls of a cylindrical channel. So if we have a cylindrical channel, something like this, with the water just flowing straight down, and we have some perimeter, which is just the interior perimeter of the pipe or the channel that is in contact with the fluid. We have the cross-sectional area, and we also have some length of the pipe, delta x. So we can say that using a force balance equation, that the mass times gravity, the force of the fluid moving down, is going to be equal to rho times our delta x times our area. And this is just the volume of fluid, so our density times volume times g. And then that is also going to be equal to our shear stress times our wetted perimeter. So the shear stress times the wetted perimeter of the pipe. Times our length of the pipe. So we can cancel out these delta x's and then divide this a across, and we're left with rho g equals our shear stress times our wetted perimeter over our cross-sectional area. So now looking at this term for the wetted perimeter divided by the area, we know the wetted perimeter is just our circumference because the entire cylinder is filled with fluid. And then our area is pi d squared over 4. And then all of this is just going to be equal to 4 over d. And then we can plug that back in over here. We have rho g. It's going to be equal to tau. There we go. That's tau. Tau times 4 over d. And then if we divide across by rho, our density, we're just left with g equals tau over 4 d. 4 d rho. And we can go ahead and plug that back in in our expression up here, g sine theta. So we will have oh, that was a very wispy tau. Tau 4 over d rho is going to be equal to 2f v squared over d. And then we can multiply across by d. We're left with 4 tau over rho. It's going to be equal to 2fv squared. And then I just forgot to put in the sign here. That doesn't change much so far. And then we're going to go ahead and solve in terms of tau. So we're going to multiply across by rho. Here, you know what? We'll have tau times 2fv squared times rho divided by 4 sine theta, which is going to be equal to fv squared rho over 2 sine theta. So now we're going to do the same thing, but this time for our rectangular channel instead of our cylindrical pipe. We're going to have rho g equals tau times our wetted perimeter over our area. And it's the same thing, but this time our wetted perimeter is going to be equal to 2 times our height, because we have both sides of the channel here and here, plus our width, and then our area will just be our height times our width. And we'll plug this in for tau. So we'll have rho g, let me retry that rho. Rho g is going to be equal to fv squared times rho over 2 sine theta. Wetted perimeter is 2h plus w, and then our area is just hw. And then these rows cancel out, and that just leaves us with fv squared over 2 sine theta. Oh, and these two, well, no, we'll leave it. Fv squared over 2 sine theta times 2h plus w over hw. It's going to be equal to our g. And then we can use this in Python to help solve this numerically. And then we were actually given the volumetric flow rate in the video Q, and we know that velocity is just Q times our, or divided by our area, in this case HW. So we can plug that in up here to up here for our velocity, and we'll be left with our fanning friction factor, or well, sorry, gravity G equals our fanning friction factor times Q squared times 2h plus w over 2 sine theta, and then we'll have hw cubed. All right, and then we're going to go ahead and use Python to solve this. One thing to note is that this fanning friction factor, we're going to use the Churchill's equation to calculate that again using the Reynolds number. But we did this in a previous video, so we'll be able to just pretty much copy and paste that. And then we're going to use SciPy Optimize, the root solver, to solve this equation. So now we're ready to start coding. I just have our basic information in here, and then our imports, and I'll go ahead and run each of these. And then, as I mentioned, we already made an expression for the Churchill equation in a previous video, so we're just going to go ahead and use that. All right, and then from there, we need to define our equation, and actually let me pull up the notebook here. We're going to be making an equation where we enter the input's going to be the height, and then we're going to be using the root solver to iteratively guess the height and solve it numerically. So we're going to have an equation. The input is going to be a vector, just so it works with the root solver. We're going to have h be the, oh, let's try this again. we're going to have h be the first and only term in that vector. And then we can go ahead and start defining a few different variables here. We'll start with just our volumetric flow rate. We have Q is equal to V times H times W. Rather, this velocity will be V equals Q over HW instead of in terms of Q, just because we're going to use it to calculate the Reynolds number and avoid some extra math in there. And then we just need to come up with a diameter to plug into the Reynolds number, which is just going to be 4 times H times W divided by 2 times H plus W. And this is the diameter that we obtained before using the wetted perimeter in the area. And then we just need to calculate the Reynolds number so we can plug it into our Churchill equation up here. Reynolds number will be rho times V times D divided by mu. And then we can plug that into our Churchill to solve for our fanning friction factor. So F will be Churchill 1H, okay. And then our Reynolds number, and then we need to come up with something for the roughness, so we'll just go with 1E -6 for now, and that should be good enough. Yeah, and then we want to return our expression here for G. So we have F times, where's our final, there we go, F times Q squared times 2, or let me put this in parentheses, times 2 times H plus W yep, and then divide that by 2 times MP sine theta. Do I have theta? Yep, I have theta defined. Sine theta times our height times our width cubed. And then the denominator needs to all be in parentheses. And then we'll put all of this in parentheses. All right, and then from here we can just use the root solver to solve this equation. All right, and then we just need to do the root solver. And then we need to provide our equation and our initial guess in the form of a vector. So we'll say 0.1 meters for now and see how that does. And it's giving us a really weird answer here. Well, first off, I need to put these in brackets. Oh, I just forgot to subtract. So we need to subtract this expression from G, so the other side equals 0, because that's what the root solver is trying to bring closer to 0. And hopefully that should fix it. Yep, there we go. So that is the height of the fluid in the channel.